Hey, Trice here. We're doing the first video for the Alum post lab. We'll start by examining the crystal formation. So as you can see, there's a lot of small crystals. Some are larger than the other. I'm not sure why that happens. I'm guessing that maybe the larger crystals were more efficient in nucleating, and so they grew at a larger rate. But nonetheless, all of them are still pretty small, which isn't surprising, being that this was recorded 2 days after the lab. If you look at the liquid level in the solution, it hasn't gone down that much, so there's still a lot of evaporation left to do. So these will grow a lot more. The shape of the crystals is interesting. They're not cubic like a sodium chloride crystal would be, which gives some insight into the lattice structure of the alum. So that'll be interesting to explore later. But yeah, that's pretty much the progress so far with that. Now let's talk about how we got to this place. So the chemistry behind the crystallization of alum, it starts with elemental aluminum, which we used in the form of aluminum foil. We dissolved that in a strong base, potassium hydroxide. This gives us the AlOH4 anions in the solution. These anions ignore the potassium in that. The anions here then react in steps 2 and 3 with sulfuric acid. In step 2, this causes the precipitation of aluminum hydroxide. And step 3, which we merge together by just pouring all of the sulfuric acid in at one time, then neutralizes the aluminum hydroxide, and the aluminum hydroxide dissolves back into the solution. From here, we have all of these species down here in the solution. And what we do next is we cool the solution to make it completely saturated very quickly, and a large amount of the alum precipitates out in the form of fine white crystals, which is represented here. From there, we take those crystals, we use those to, we rinse them, get them cleaned up, and then we use those to make a saturated solution. In this case, we did that in ethanol and water. And the reason it has to be saturated is that when solvent evaporates out of that solution, it precipitates slowly large, larger, clearer, higher quality crystals, as can be seen here. Now, to make sodium chloride crystals, the difference would be we wouldn't start with a elemental metal like aluminum. We would just start with hydrochloric acid and sodium hydroxide and mix those two together to create a neutralization reaction where we would get aqueous sodium chloride and H2O. And now from this spot, and this is on the U of Oregon website, once we have that reaction complete, we would put this solution of the sodium chloride in water, and we would put it in an ice bath, much like we did with the alum, and we would see the solution quickly become saturated and the smaller sodium chloride crystals precipitate out. From that point on, it'd be the same steps: rinsing the crystals, creating a saturated solution of sodium chloride, and then transferring that into the vial, putting the chem wipe over it, and allowing this solvent to evaporate out, forming the larger sodium chloride crystals.
Another way to form crystals of a different material comes from Scientific American, and they tell how to make a borax crystal, but to make it on a string, which is how it differs from how we did it. So what you do, you start similarly. You use store-bought borax and make a saturated solution of that, and then you either cool it in an ice bath or you allow the solvent to evaporate slowly off. But it differs in that a string is hung into the solution from a pencil, and this plays into the idea of nucleation that Professor Nez talked about, and that the crystals are given more surface area to nucleate on the string as opposed to how they nucleate in the vial, just at the bottom of the vial.